Okay, any questions from the previous class? Check, check. Check. Am I audible at the back? This doesn't seem to be working. Hello, hello. Hello, hello. So everybody at the back can hear me, right? If not, please come forward. All right, so let's continue where we stopped last time. In the last class, we saw this problem of analyzing tail bounds for norms of sub-Gaussian random vectors. All right, and in particular, we showed that the norm of a sub-Gaussian random vector is also a sub-Gaussian random variable, and the sub-Gaussian norm of norm x minus square root of n, assuming that the vector x is a zero mean sub-Gaussian random vector with unit variance, with each entry having unit variance. The sub-Gaussian norm of this vector is upper bounded by c times the square of the largest sub-Gaussian norm. Right? And then we use this to derive a result for dimensionality reduction. So we showed the Johnson-Linden-Strauss lemma, which said that you can do dimensionality reduction for n points which lie in a very high dimensional space of dimension capital D. You can bring this down to little d as long as little d is greater than or equal to something times 1 by epsilon square log n by square root of delta. All right. And this, in fact, can be achieved using a simple linear projection. So there exists a random linear projection such that you can get an epsilon isometry as long as the dimension d is at least this much. All right. And in fact, you can also, so this is sort of an achievability result. It tells you that there is one way of reducing the dimension from capital D to this particular little d. But it can also be shown that this is almost essentially tight. You can't do too much better than this, no matter what other approach you use. Right? So in some sense, this is almost optimal. You may be able to improve things in terms of constants and perhaps a little bit slightly improve these exponents over here, but you will not be able to significantly improve over this value of little d. So far what we've basically seen is ways to derive concentration bounds on random variables, sums of random variables, and slight variants of these. So we looked at random variables which could be represented as sum of squares, for example. But we didn't go much beyond any of those. So today we'll look at a very general approach that allows us to derive tail bounds on more general functions of random variables. So first we'll see a very general bound, but we'll also see specializations of that to classes of functions. All right. So let's see what makes sums of random variables sort of special. What is it that allows us to derive these nice exponential tail bounds? So firstly, one observation is that if z is, let's say, the sum of n IID random variables, or let's say n independent random variables, each with say constant variance, then the variance of z is nothing but the sum of the variances of the xi's, right? and if the variance of each xi is some constant, then the variance of z is n times some constant. All right, but then you can't really say that for a more general function of random variables. Right, so suppose z is some g of x1 through xn, where x1, x2, x3 up to xn are all independent random variables, then you can't really make this claim. It could, depending on the function g, it could be very general. All right. So, but we'll use a generalized approach to express the variance as a sum of terms that look like this. Right? Of course, it's not equal. You can't really say that it is the sum of the variances of the xi's, but we'll still try to, in some sense, decouple the terms or the influences corresponding to the individual random variables. Right? The nice feature about this particular expression is that the variance can be decoupled as a sum of variances of individual random variables, and we'll try to do something similar, not exactly the same, but some sort of a similar approach. All right. So firstly, let's write down what we mean by expectation of z given x1 through xi. All right. So this conditional expectation, I'm assuming that z is some general function g of x1 through xn. All right. So expectation of z is nothing but expectation of g of xn given x1, x2, x3 up to xi. All right. And this is nothing but an integral that where you're taking the expectation with respect to xi plus 1, xi plus 2, and so on all the way up to xn, but conditioned on x1 through xn. All right. So it's nothing but the expectation taken with respect to this particular distribution f of xi plus 1 through xn conditioned on x1 through xi. All right. This is something that you have to keep sort of make note of. All right. So our goal will be to express the variance in terms of the conditional variances, in some way. All right. While at the same time trying to decouple the influences of individual random variables. So to do that, I'll define this quantity delta I, which is expectation of z given x1, x2, x3 up to xi minus 1, minus expectation of z given x1, x2, x3 up to xi. So this should be with respect to xi. So expectation of z given x1 up to xi minus expectation of z given x1 up to xi minus 1. All right. So basically this term is a function of x1 up to xi. Right? It's a random variable. A conditional expectation is always a random variable. And this is a random variable that depends on x1 up to xi minus 1. If I tell you what the value of x1 up to xi minus 1 is, then there's no more randomness present in this particular quantity. On the other hand, this term is a function of x1 up to xi minus 1. All right, so there's some more randomness present in the first term compared to the second term. All right. So let's look at the quantity summation I equal to 1 up to n delta I. What will this be equal to? I'm sorry? So z is this function, right? It's any function of x1 up to xn. So g is fixed, and we know what g is. For it could be anything. For example, g could be the sum of x1 through xn. It could also be, let's say, the maximum of x1 through xn, or the minimum of x1 through xn, or I don't know, the norm square of x1 through xn, anything, any function.
So that would be e of z given xn minus
Okay,
x1 to xn minus of first x.
correct. So basically, if you think about this, this is just a telescoping sum. Right? So this will be expectation of z given x1 up to xn minus expectation of z. Right? But what is expectation of z given x1 through xn? It is just z itself. Right? So this is nothing but z minus expectation of z. Okay. So I can write the variance of z, which is nothing but expectation of z minus expectation of z the whole square, as expectation of summation I equal to 1 to n delta I square. Right? This is equal to, if I just expand the square of the sum, this is equal to summation I equal to 1 to n delta I square plus expected value of sum overall I, sum overall j not equal to I, but let's say j not equal to I, delta I, delta j. Right? But this is equal to expectation of summation I equal to 1 to n delta I square plus 2 times expectation of sum overall I, sum overall j greater than I of delta I, delta j. Do you agree with me? Okay, fine. Nothing fancy so far, just straightforward. The first term is nice, so let's keep it aside. Let's see what happens to the second term.
So,
Yeah.
so expectation of z given x1 to xn should be a constant, right?
Expectation of z given x1 through xn.
But if I know x1 to xn z, I know z. And z
So
is
given
constant.
x1 through xn, you know z.
But that's not conditional.
No, right? So the conditional expectation, this particular conditional expectation is a random variable that depends on x1 through xi.
Okay, so it's different.
Right? So this is the expectation of z given x1 through xn. I mean, that's why. So you just look at this particular expression. Right? You're integrating with respect to everything else except x1 up to xi. Right? So expectation of z given x1 through xn is expectation with respect to everything except x1 through xn, which is z itself. Right? Okay. So this term is okay. Let's try to analyze what happens to this particular term. Let's look at each one of those terms in that sum. So fix any I and j which is strictly greater than I. I want to see what happens to expectation of delta I, delta j. Okay, so let's write that down explicitly. This is expectation of what is delta I? It is expected value of z given x1 up to xi times expectation of z given x1 up to xj. All right.
Minus expectation of z.
I'm sorry, minus. Yeah, right. You're right. let me expectation of z given x1 up to xi minus expectation of z given x1 up to xi minus 1 times expectation of z given x1 up to xj minus expectation of z given x1 up to xj minus 1, right? So this I'll write this. What is important to note here is that this quantity delta I is a function of x1 up to xi, right? And this is a function of x1 up to xj, where j is strictly greater than I, right? So let me first condition on x1 up to xi and then see what the residual is in terms of x1 xi plus 1 up to xj. Right? I'm just using the Tower law of expectation over here. So expectation of, I can write expectation of delta I delta j as expectation with respect to, now when I write expectation over here without any qualifier, it means that I'm taking the expectation with respect to x1 up to xn, right, in general. So I can write this as expectation of expected value of delta I delta j conditioned on x1 up to xi, right? And basically this outer expectation will then be over x1 up to xi, right? So first I'm taking the expectation with respect to everything except x1 through xi, and then finally I'm taking the expectation with respect to x1 through xi. No, I want to take it with respect to x1 through xi. All right.
J is greater than n.
Correct.
Then why should I be taking J?
What do you mean, why should we take j?
The second term is x1 to xj and j is greater than n.
Correct.
So why shouldn't you condition on j, x1 to xj?
What do you mean, why should we condition?
Why shouldn't we?
Why should, because that expectation is taken care of by this outer expectation, right? So this outer expectation will take care of all of the remaining so this inner expectation, okay, so so this is a function of delta j is a function of x1 through xj, right? Delta I is a function of x1 through xi. When I'm taking the expectation over here, effectively I'm taking expectation over x1 through xj, because j is greater than I. These two combined depend only on x1 through xj, right? I'm decomposing this in this expectation into two parts. So in here I'm taking the expectation with respect to xi plus 1 through xj, conditioned on x1 through xi, right? So basically this expectation is with respect to the distribution f xi plus 1 up to xj given x1 through xi. whereas this expectation will be with respect to the distribution fx1 through xi. All right. Is this clear? Fine. Now, this is expectation conditioned on x1 through xi. Right? So here I am taking expectation only with respect to xi plus 1 through xj. Right? Which means that delta I does not depend on this particular distribution, because it's a function of x1 through xi, and I'm not taking the expectation with respect to x1 through xi. So effectively I can take this outside this particular expectation. All right. So this is equal to expectation of delta I times expectation of delta j given x1 through xi. Right? So this is expectation of delta I times expectation. Now again, it's quite cumbersome to write everything, but still let's write it down to understand what this is equal to. Maybe to remove some of the clutter, let's analyze one of these terms, just this quantity, expectation of delta j given x1 through xi for some j which is strictly greater than I. It's at least I plus 1. Right? So this is, which one? Because delta, so here this expectation operator is with respect to the distribution you're averaging over xi plus 1 through xj. Which one? Because that's how I've decomposed this expectation, right? So first I'm going to take expectation with respect to xi plus 1 through xj, and then I'm going to take expectation with respect to the remaining variables x1 through xi, because we conditioned on x1 through xi. It's sort of a trick that I'm playing over here. All right, and we'll see why I'm playing that trick in just a little bit.
The outer one should be x1 to xi or x1 to xj. The outer with respect to.
It is with respect to x1 through xi, because xi plus 1 through xj is taken care of by this inner expectation. So then totally I have taken with respect to all the j x's, right? So this is expectation of delta j given x1 through xi, which is expectation of, again if you remember what delta j is, it is expectation of z given x1 up to xj minus expectation of z given x1 up to xj minus 1. And this outer expectation is conditioned on x1 up to xi. Right, this is expectation of delta j given x1 through xi. So this is nothing but expectation of expected value of z given x1 through xj given x1 up to xi minus expectation of expected value of z given x1 up to xj minus 1 conditioned on x1 through xi, right? But what is this equal to? One to. So remember that j is strictly greater than I. Correct. So basically this is as though you are taking expectation with respect to everything else from I plus 1 through j. So what remains is just expectation of z given x1 up to xi. Right? You should remember that this is, when I say this expectation is with respect to f xi plus 1 up to xn given x1 up to xi. Right? So expectation of anything, let's say w with given x1 through xi is nothing but integral f xi plus 1 up to xn given x1 through xi of xn times w right, xn given x1 through xi times what is w? It is expectation of z given x1 through xi. Sorry. So by w in this case is this particular quantity, expectation of z given x1 through xj, and expectation of z given x1 through xj is equal to so this is xi plus 1 up to xn times this is expected value of z given x1 up to xj. So this is times f x j plus 1 up to xn given x1 up to xj times z, which is g of x1 through xn dx. Yeah.
Can you just recap what you've done so far?
Right. So basically what I want to compute is expectation of delta j given x1 through xi. Let's forget about everything else for now. Let's just look at one of these terms. Expected value of the first term, expectation of z given x1 through xj, conditioned on x1 through xi. Right? So here I am taking the expectation with respect to everything else from j plus 1 onwards. Right? And here I am taking the expectation with respect to everything from I plus 1 onwards.
So I can say that in the LHS, the expectation is taken with respect to x1 through xj.
The left hand side, the expectation is taken over xi plus 1 up to xn, right?
No, in the initial expectation of
Here, yeah.
Yes. Is it taken with respect to
Everything.
with respect to everything?
Correct.
Good.
Correct. Everything from 1 to n. But I'm breaking that up into two. First, I'm taking the inner expectation is from I plus 1 onwards. And the outer expectation is with respect to what is remaining, which is 1 to I. Right? And basically, I'm doing the same thing. So if it helps, just assume what would happen if all of these xn, xi's were independent random variables. Right? What would that mean? It means that I'm taking this expectation from, with respect to everything from I plus 1 onwards. Right? So here this outer expectation is with respect to everything from I plus 1 onwards. This inner expectation is with respect to everything from j plus 1 onwards. Right? So this outer expectation would be from I plus 1 up to j. Right? So what would this overall expectation be? I plus 1 onwards, right? So that would be nothing but expectation of z given x1 through xi. That's all there is. It is just that there are too many variables which may be sort of confusing you, but effectively that's it. It's nothing but the Tower law of expectation. So that's the first term, right? What about the second term? Again, j is strictly greater than I, right? So j minus 1 is at least I. And this inner expectation is from j up to n. And this outer one is I plus 1 up to n. So what remains is just expectation of z given x1 through xi. That is all. Right? I'm doing nothing else but just play around with these expectations and conditional expectations, nothing else. Right? It is just that the notation gets a little confusing. So what is this equal to? It's 0. So expectation of delta j given x1 up to xi for j strictly greater than I is equal to 0. Now if I go back here, what I've shown is that this quantity is equal to 0. So this quantity is 0. So expectation of delta I, delta j for any j strictly greater than I is equal to 0. Right? Now again, if I go back to my expression for the variance, I've just shown that this quantity is equal to 0 for every pair I comma j with j strictly greater than I. So the variance of z is the sum of the expectations of these delta I squares. So with z equal to g of x1 up to xn, the variance of z is equal to summation I equal to 1 to n expectation of delta I square, where each delta I is nothing but expectation of z given x1 up to xi minus expectation of z given x1 up to xi minus 1. Right? So I made no assumptions on the xi's, right, so far. I've done nothing else except assume that z is some function of x1 through xn. I didn't even really need x1 through xn to be independent of each other. But even then, I can say that the variance of z is equal to summation I equal to 1 to n expectation of delta I square. So it's a sum of some things that look like variances. All right. Each of these delta i's, I don't say that delta 1 and delta 2, for example, are independent of each other. That's not the case. Right? But the nice thing is that these delta i's are all look symmetric. So delta 1 and delta 2 are kind of symmetric with respect to each other. And the variance is a sum of such terms. Okay. Now it may seem that we've not done much except some mathematical jugglery. Right? I've started with something and then I ended up with some expression, and I don't even know how to handle this in general. But this will be the starting point for a number of very powerful inequalities. Okay? So the first sort of approach that we'll use is we'll try to see what happens to each of these expectation of delta I squares, right? Because as of now, it doesn't really appear very symmetric because delta 1 is a function of x1, delta 2 is a function of x1 and x2, delta 3 is a function of x1, x2, x3, and so on. But I'll manipulate this to make sure that each term, so I'll try to express the variance as a sum of many terms, where each term is almost looks like the other. All right.
What is symmetric?
So symmetric, for example, say each term depends on just let's say the term 1 depends only on x1, term 2 depends only on x2, and so on. If g of x were a sum of independent random variables, then the variance of z would be the sum of the variances. So I could write this as expect variance of x1 plus variance of x2 plus variance of x3 and so on. Right now I'll do something else. I'll write it as a sum of variances, but each of those terms will depend on everything else except xi. All right. So in the case of sum of random variables, you can express the variance as a sum of the variances where the ith term depends only on xi. Now my goal will be to express this as a sum of terms where the ith term depends on everything else except xi. In that sense, it looks symmetric. How this will be useful, we'll see that later on, but it gives us something nice to work with. Okay, so we'll start with expectation of delta I square. So expectation of delta I square is just this expectation of expected value of z given x1 up to xi minus expectation of z given x1 up to xi minus 1. So in fact, let me start with something more basic. Let's just start with delta I square. All right, this whole thing square. Now, what is the difference between this term and this term? This depends on x1 through xi. This depends on x1 through xi minus 1. right? Which means that this does not involve xi. I've averaged out xi in the second term. Okay, so again I'll play around with this. I'll use the Tower law of expectation to write this as expectation of z minus. Now this is a crucial point where I'll make use of the fact that x1 up to xn are all independent of each other. All right. So in this case, I can write this as z minus expectation of z, where this expectation is only taken over xi. So z is a function of x1 through xn, and this term here is expectation only with respect to xi. So this quantity is integral f xi of xi g of x1 up to xi minus 1 little xi plus 1 up to xn. So this e superscript I of z is a function of all of the xj's except xi. So it depends on n minus 1 random variables.
So can you once again say from first sentence to second line?
Fine. So here, let's look at each of these terms. Again, let's assume that x1 through xn are all independent of each other. All right. Let me explicitly state that. Right, x1 up to xn are all independent. So, which means that this term I'm taking expectation over xi plus 1 up to xn. This is nothing but that. This is expectation of with respect to xi plus 1 up to xn of z. This is expectation of z with respect to xi up to xn, which is nothing but you first take expectation with respect to xi and then you take expectation with respect to xi plus 1 up to xn. That is all that I have done over here. If I complete this, x1 up to xi square. All right, so the first term here is this, right? It is expectation with respect to xi plus 1 up to xn, which is this term here. And the second term is expectation of z with respect to xi up to xn, where I'm first taking expectation with respect to xi, and then I'm taking expectation with respect to the remaining xi plus 1 up to xn. Okay. So far it's okay? Great. So now I have a square of a conditional expectation. All right, maybe whole square. All right. So this is the square of some particular expectation, but you know that the square of an expectation is less than or equal to the expectation of the square, right? Just you can either use the fact that variance of some x is expectation of x square minus expectation of x the whole square, and this is greater than or equal to 0, or it's an application of Jensen's inequality. Both are equivalent ways of saying the same thing. So this is less than or equal to expectation of z minus this expectation I of z the whole square. Where each of these terms, so here this is z as it is, but the second term is where I'm taking the expectation only with respect to everything else except xi. Sorry. So here I'm taking expectation with respect to just xi. So this depends on where?
Condition.
Right now I'm assuming that they're all independent of each other. So I don't have to worry about conditional distributions, because the conditional distribution is equal to that of the unconditional distribution. Right? That simplifies notation a bit. But up to this particular point, what I had over here, I did not even require independence of x1 through xn. But here I am making use of the fact that x1 through xn are independent. Right? So if I make use of this inequality back here, it means that for any general function g, g of x1 up to xn, where x1 and x2, x1 up to xn are independent, I have an upper bound on the variance of z. This is less than or equal to summation overall I equal to 1 to n of expectation of z minus expectation with respect to xi of z whole square. So let me call this quantity V. Right? You can say something else that I will not prove over here, but it's an easy exercise, is that you can show that this is equal to, now this is in terms of expectations with respect to xi of z, right? But I can also say something, if let's suppose that I replace xi with an independent copy. Okay, so let me define zi prime to be equal to g of x1 up to xi minus 1 xi prime xi plus 1 up to xn. Alright, so I have my z is a function of x1 through xn. It's a random variable that depends on x1, x2, x3 up to xn. Zi prime depends on x1, x2 up to xi minus 1, xi plus 1 through xn, but xi is now replaced with an independent copy. Okay. then you can show that V can be written as half of summation I equal to 1 to n of expectation of z minus zi prime square, which is also equal to summation I equal to 1 to n expectation of z minus zi prime plus the positive part square, and also equal to summation I equal to 1 to n expectation of z minus zi prime minus square. Where this x plus is nothing but max between x and 0. So if it's negative, you clip it to 0. If it's positive, then you leave it as it is. Yes.
We replace X-ray dash. So what does it resembles like? We never talked about identical. We only talked about only independent.
Correct. So x1 up to xn are all independent of each other, where x1 is distributed according to fx1, x2 is distributed according to fx2, and so on and so forth. Right? Now zi prime is now a new random variable, where x1, x2, and so on are the same except xi. But xi is a new random variable independent of x. So xi prime is a new random variable which is independent of xi and also of the remaining x1 up to xn, but it is distributed, it has the same distribution as xi.
Why is it identical?
So, I'm sorry?
Identical.
So it is identical with respect to xi. So xi and xi prime are both identically distributed.
But X-ray dash is independent to all.
Correct. Yes. The x1, the remaining xj's need not have the same distribution as xi or xi prime. But xi and xi prime have the same distribution and they are independent of each other.
So how did we get variance equals to half of z minus?
This is a claim so far. Okay. It's not very difficult to prove from the previous point, but just in the interest of time, I'll maybe skip that particular proof and I'll give you where to find the proof. And x minus is min of x comma 0. I'm sorry. Slight change, so I will use max of minus x comma 0. So it's a negative, so x minus is the negative part of x and x plus is the positive part of x. And you can write V also as infimum over all possible random variables Zi that depend on everything else except xi. Of at the face of it, it doesn't seem like I've simplified anything. right? It's just like a bunch of complicated inequalities, all right? So this is what is called Efron-Stein inequality. And at least at present, it seems like there's some bound on the variance. It's not clear as to how we can make use of this particular bound. All right. But this will be clear when I just look at another restricted class of functions. Right. So we want to. So far we know what happens for sums of independent random variables. Now we look at a broader class of random variables for which the function does not depend too much on any individual random variable. Right? For example, let's suppose that z is x1, x1 plus x2 plus x3 and so on. If I perturb xi by a little bit, it doesn't influence the sum by too much. So if I change xi by a constant amount, the variation of the sum is again not much. It varies just by a constant amount. It doesn't vary as, say, linearly with n. Right? So this is the class of functions with bounded differences. So suppose that, so f, let me not use f, let me use g. So g is a function from any alphabet. It need not even be a function over the reals. Has the bounded differences property if I can find constants c1 up to cn such that the maximum overall x1 through xn and xi prime of, so you look at g of x1 through xn and you replace xi with an xi prime, any other xi prime. Then the maximum variation is Ci. So irrespective of the rest of the values, if you replace xi with xi prime, then the maximum deviation is Ci.
Is there something like how far should xi find?
Nothing.
But you said xi is identical with xi.
So right now, this particular statement is for the function. There's no distribution, nothing over here. All right, so there's no notion of independence or dependence. It's purely a property of the function. So for example, if
Sir, here x1 to xn are random variables.
x1 through xn are just variables. That's it. Yeah. So let's look at xn. Of course, I also need to specify what the alphabet is. All right. So let's say that this g of x1 through xn is say 1 over n summation I equal to 1 to n of xi, and each xi is allowed to be anywhere between 0 and 1, or let's say minus 1 and plus 1. Okay, so this is one function, and each xi can be anywhere between minus 1 and plus 1. Then this satisfies, then if I replace xi with any other xi prime, by how much can the function g deviate? So what is g of x1 through xn minus g of x1 through xi minus 1 xi prime xi xn? What is this equal to? Correct. So basically this is equal to xi minus xi prime divided by n, which so this absolute value can be at most 2 by n. Right. That's one thing to keep in mind, is that's because I restricted each xi to only take values between minus 1 and plus 1. If I didn't have this restriction, suppose xi can take any real value, then it does not satisfy the bounded differences property, because this quantity is never bounded. All right. But the point here is that as the number of variables keeps increasing, so this bound is fixed, but the number of variables, if this keeps increasing, then the difference keeps decreasing. That's the nice feature. All right? That is what typically that helps us a lot in deriving these concentration inequalities. So essentially, the influence of any one single variable is not too much. Okay. Great. So now we've defined these functions with bounded differences. Let's try to use the Efron-Stein inequality to see what happens to a function to sort of bound the variance of any function with bounded differences. So for any g that satisfies the bounded differences property with constant c1 up to cn, right? If I use the Efron-Stein inequality, I have the variance of z is less than or equal to, if you recall, the last one was you replace any xi with an independent copy xi prime. I'm sorry. So you look at zi to be any random variable that depends only on x1 through xi minus 1 and xi plus 1 up to xn. It does not depend on xi. Of summation I equal to 1 to n of expectation of z minus zi the whole square. This depends only on x1 through xi minus 1 and xi plus 1 up to xn. So if zi depends on, let's say, everything else except xi, I could take zi to be equal to let's say g of x1 up to xi minus 1, some fixed value, let's say xi prime, xi plus 1 up to xn. Right? In principle, I could just do this. If I do that, then what is the maximum value that z minus zi can take, or z minus zi the whole square can take, because it satisfies the boundary differences property? Ci square, right? So this implies that infimum zi of expectation of z minus zi square can be at most ci square. So the variance of z is upper bounded by summation I equal to 1 to n ci square. Okay, so how does this help? It helps because now if the influence of any one random variable is not too much, then basically this variance is upper bounded by n times some constant. Right? Again, remember that g is not necessarily a sum of random variables. It's any arbitrary function that satisfies the boundary differences property. It could have a very complicated structure. But even then, the variance of z is n times some constant, which means I can now use something like Chebyshev's inequality. So just because I have an upper bound on the variance, Chebyshev's inequality says that the probability that the deviation from the mean is some delta is upper bounded by the variance divided by delta square. Right? So this helps us a lot.
So this is for only bounded differences problem.
Correct. So this was where I applied the Efron-Stein inequality to a function with bounded differences.
Where else can we use that?
We can. So in fact, you can relax this to an even more general class of functions. Again, with similar kinds of properties. Functions, so-called functions with not bounded differences, but what are called self-bounding functions. But maybe before I go to that, I'd like to point out that now that we have this, some observations related to these functions with bounded differences. So firstly, you can show that, not very difficult, if G has the bounded differences property, then the variance of Z, you can improve this constant to 1 by 4. This is 1 by 4 summation I equal to 1 to n ci square. Doesn't give too much of an improvement, but it's some constant improvement. The second, now potentially you can use Chebyshev's inequality. To show that the probability that Z minus expectation of Z the probability that this is greater than or equal to delta is less than or equal to the variance, which is 1 by 4 summation I equal to 1 to n ci square divided by delta square. But for this you can prove something even stronger. So this only gives a polynomial tail bound, but if it satisfies the bounded differences property, you can show that this greater than or equal to delta can be upper bounded by 2 times e to the power minus 2 delta square divided by sum over I ci square. So in fact, if a function has the bounded differences property, then it's in fact sub-Gaussian. Right? So it's not just that sums of sub-Gaussian random variables are sub-Gaussian, but in fact, any function of random variables which satisfies the bounded differences property is also sub-Gaussian.
Over there, they have substituted variance with 1 by 4 summation of
Correct.
CS. I mean, I understand it's constants and summation of constants,
Correct.
but it is still now a more linear boundary because variance is less than that.
True.
Why did we do this?
Well, because this is deriving the McDiarmid's inequality involves a lot more sophistication, but this is just one way we could apply the Efron-Stein inequality to functions with bounded differences. Right? It came almost as a corollary of the Efron-Stein inequality. But the Efron-Stein inequality is a lot more powerful and also can be used in cases where you cannot prove exponential tail bounds. Because over here, right, to derive the Efron-Stein inequality, I did not require any assumptions on the function g. This holds true for every function g of as long as x1 up to xn are independent of each other. Right? So even though g may be very complicated, you may not even have a closed form expression for g. Even then you can make use of the Efron-Stein inequality. Okay. So, yeah. So maybe let us have maybe 10 minutes. Let's see what I can. Right. So let's do a quick example to see where Efron-Stein's inequality can be used, or even sort of the bounded differences property can be used. Right. So the problem is the following. You are given x1 up to xn, which are numbers, right? Each xi takes values between 0 and 1. Okay. You can think of this as in the context of, let's say, workloads that have to be assigned to servers. Right? Maybe each xi could represent the time required to complete a particular task. The time or some resources required to complete the ith task or the ith job. Okay, they can be arbitrary at the moment, and I want to know what is the minimum number of servers that are required to satisfy all of these n jobs. Okay, so basically each server, assume that I have any number of servers. I can give you any number of servers, but each server has a total resource of one unit. Server has, let's say, capacity 1 unit capacity. All right. This capacity could be, I don't know, maybe the number of cores or the time for which you can run this, and so on. Okay. So for example, let's I could assume that if you take one example, let's say x1 equal to 1/3, x2 equal to half, x3 equal to let's say 9/10, and x4 equal to 2/3. x5 equal to let's say 3/7. Okay, what is the minimum number of servers that I would require to satisfy this? I could potentially group x1 and x4 together into one server. I could group x2 and maybe x5 into another server and assign x3 to a third server. Right? So I could satisfy this particular requirement using 3 servers. But again, so given any such requirement, there's some way you can potentially numerically compute the minimum number of servers by just running through all possible combinations. Right? But remember that the total capacity that the server has is unit. So you cannot assign, let's say, these two jobs, you cannot assign, let's say, these two jobs to the same server, because the total resource requirement for this would be 9/10 plus half, which exceeds 1. Okay. So let g of x1 up to xn be the minimum number of servers required to complete these tasks x1 through xn. The main point here is that this function g is complicated. I don't have a closed form expression for this. All right. Now in this case, I want to know. Let me give. Let's assume that x1, x2, x3, and so on are jobs that are coming in, and these xi's could be modeled as random variables according to some distribution. Okay. So x1 up to xn are, let's say, IID. Some distribution. Now in this case, what can I say about the variance of g of x1 through xn? Yeah? I don't have a closed form expression for g, right? So it's in general, it's going to be hard to compute the variance of g. I don't have a way of computing the closed form expression for the variance. All right? But let's take g, okay? And suppose that I replace any xi with some other xi prime. By how much can the number of servers required change? So given any x1 through xn, if we replace any one job with xi prime, then by how much can the number of servers required change? 1, right? Because maybe if xi prime requires more resources than xi, at most you would require one more server. Or if xi prime is less than xi, you would need to remove one of the servers. Right? So g of x1 through xn, g of x1 through xi minus 1, xi prime, xn, this can deviate by at most 1. So this function g, although it's very complicated, I don't have a closed form expression, this satisfies the bounded differences property with constant 1. So what can I say about the variance? Just by the Efron-Stein inequality, it is summation I equal to 1 to n, 1/4 times ci square, which is 1, which is nothing but n by 4. Right, so this is an example where I could very easily compute a bound on the variance. But in this particular problem, computing a bound on the expectation is hard. Right? So, yep, you're right, that finding a bound on the for many of such problems, finding a bound on the expectation can be very, very hard. There could be ways of doing it, let's say numerically. That requires a lot of effort. But once you get a bound on the expectation, now getting a bound on the tail probability is easy, because I already know what the variance is. But what I also know is if I have some idea of how much the expectation can be, right, then this becomes easy to handle. So let's say if I have a distribution for which expectation of z is something that grows linearly with n, which is kind of believable, right? If I have n jobs, then the number of servers that I would require would scale proportionally with n, because all of the jobs are independent of each other. So that much is okay. Then the probability that z minus expectation of z is greater than or equal to some delta times expectation of z is less than or equal to the variance square, which is n by 4 times delta square expectation z the whole square, right? Which means that the numerator has n, the denominator now has n square by 6. The numerator has n by 4, the denominator has something that is proportional to n square. So this decays as 1 over delta square n. Right? So if I have some way of estimating the expected number of servers required to satisfy these jobs for this particular distribution, then I don't have to worry too much. I just have to give a small amount of slack, and with high probability I'll be able to satisfy all of the jobs. I don't have to worry about the requirement deviating too much from the expected amount. On the other hand, if I didn't have this particular bound, and somehow I was able to calculate the expected requirement, expected number of servers required, then I may have to give a much higher additional tolerance, just to make sure that with high probability I can satisfy all of the demands. This tells me that I don't need to go too much beyond the expected value. The probability that the number of additional servers required will be too much is not too high. It's vanishing as n becomes larger and larger. All right. So this gives you ways in which, I mean, this was of course using the Efron-Stein inequality, but I could have also used McDiarmid's inequality to in fact show that this is an exponential tail bound. All right. So these tools are very, very powerful. We've just scratched the surface of what we can do with tools like these. It goes well beyond just self-bounding functions, but even with self-bounding functions, you can do a lot more than what you could do using just sums and averages of random variables. Okay, so let's stop here. Any questions?
So the expectation maximum number of servers which can be required is at most n.
It's at most n. I agree.
So obviously it will be proportional.
But it could be much smaller than n, right? In principle.
Just assume the worst case.
The worst case, I agree.
Worst case will also be scaling by.
But remember, if expectation of z is much smaller, then this upper bound is very loose, right? But because they're all independent of each other, as long as the distribution of each xi does not depend on n, right? In principle, the distribution of xi could also depend on n. But right now, if we assume that that each xi, the distribution of xi does not depend on n, then you will indeed have expectation of z proportional to n.
And what are self-bounding functions?
So maybe we'll continue that in the next class because it will require me some time to explain what they are. But in a way, they generalize functions with bounded differences. All right. Okay, so let's stop here.